All right. Welcome everybody to a two-stage session of the RQI North Online conference. Our first speaker, I have the pleasure to introduce Magdalena Zych from the University of Queensland. Magdalena is going to talk about operational models of temperature superpositions. Magdalena, whenever you want, the floor is yours. Pleasure to have
you. Thanks, Eduardo. And again, many thanks to all of you who contributed their time to organizing this event. It's really very valuable for the community to have these events going even in these times. And yes, so the topic I would like to talk today is perhaps not the usual one we would see, and I hope it will be interesting for you. Okay, it's already something. All right. Just to start, I just wanted to give a quick note to the many collaborators on various projects that we do here at UQ. But in particular, I would like to highlight the names of two PhD students that have just recently submitted, Caroline Wood and Harshit Verma, because the results I'll be presenting is their joint paper. So if you look for excellent postdocs, and get in touch with Caroline and Harshit. Here at UQ, among my students and collaborators, we look at various questions that relate to quantum and gravity. And this work is also embedded in that context. So I thought to maybe just very briefly clarify where we stand in that field, because there are many various incarnations of that research. And so people would often think of some tests of general relativity with quantum systems when one hears about quantum and gravity together. Of course, quantum gravity as such, that's a major endeavor in theoretical physics. And what we are interested in is the overlap of the two theories from the perspective of some fundamental tests. So how could we test physics where both quantum mechanics and in particular of interest is relativistic gravity effects would come into play, and how such effects can impact future high precision quantum technologies. So technologies like trapped atom or ion based quantum clocks or simulators. There are also topics of interest at the intersection of quantum information and relativity, and that can be kind of quantum controlled channels, and that can include also some scenarios where one could have some quantum degree of freedom associated with the metric, and try to understand to which extent we can apply standard tools that we have to understand what phenomenology we might encounter in such scenarios. We also look sometimes at some alternative gravity models and what are their implications and how they could be tested. And the typical tool of choice among my works is a composite quantum particle. And the reason is that such particles are, of course, idealized models of many different tools that we use in research. So a composite quantum particle can be a model of a clock. So the particle moves along some word line and internal states evolve according to the proper time of the word line. And once you start to deal with quantum systems, the notion of a word line acquires a quantum description, and that context becomes interesting. The internal quantized states of a composite relativistic particle actually through their internal energy contribute to the total mass energy of the particle. So such particles are also ideal as quantum test masses for tests of Einstein equivalence principle. And here I want to stress that when we talk about quantized test mass, what we actually mean by what is actually quantized is the mass, in a sense, of the total mass energy of a particle. And this approach allows some new insights into the very question of how one would formalize validity or violations of the Einstein equivalence principle for in the context of quantum theory. Such particles can, of course, interact with external environments, and so they also can model something like an Unruh-Levy detector or a toy model of atom-light interactions. And many of you would work directly within such models. So I'd like to highlight at this point that tomorrow, Carol and Evan Gale, who is a PhD student current in my group, they will be both talking about what can we learn from considering the models of an Unruh-Levy detector, where we quantize the center of mass and where we either consider relativistic corrections to the non-relativistic description of it, or we include the full relativistic dispersion relation in first or second quantization even. So if you want to learn what happens, please make sure you don't miss their talks tomorrow. And such particles can also be, of course, coupled to thermal environments. And so they can model an idealized thermometer. And that's what I would like to talk about today. And so why would we like to talk about some quantum features of temperature, some superpositions of thermometers? So I guess in this conference, there might be people somewhat familiar with Tolman-Ehrenfest effect. So just very briefly, that's a result from classical general relativity, essentially saying that when we have some extended system in thermal equilibrium in the gravitational field, locally measured temperature is not constant, and that can be looked through the lens of time dilation. And so now a natural question arises: if we have such extended thermalized system, for example, air in the Earth gravity, and we have some quantum particle whose internal states can thermalize with that environment, but where the center of mass is not classical, but can in particular be prepared in superposition of various locations. The thermometer then interacts depending on the state of the center of mass with different baths. And so the question arises, what such a thermometer will measure? Another natural context for such considerations, and in some sense they were also inspiration for this work, is Unruh effect, where again, just very briefly, we can say that an accelerating agent would see some thermal environment where inertial one would see vacuum of a relativistic field, and this temperature depends on the acceleration. And so, of course, we can have agents, and in particular, Unruh-Levy detectors that could be described as moving in superposition of trajectories with different accelerations. And then again, the question arises: what temperature would be measured? And I highlight these two motivations because I'd like to go back to them at the end with perhaps some surprising conclusions and insights into what might be going on in these two scenarios. Sorry, so that's just a little cartoon for a detector in superposition of accelerations. But let me maybe start the main part of the talk with just a little reminder about how we describe thermalization processes. So I'll through this talk mostly talk about idealized scenario where we have some channel, here denoted with capital epsilon, that leads to a complete thermalization of a system that is initially prepared in some tensor product, so independently of the state of a bath. The bath is in a thermal state, and this channel gives, as a final state of the system, a thermalized state at the temperature of the initial temperature of the bath. So such channel can be described through some joint unitary operator acting on both bath and the system. Importantly, it's only defined up to some isometry on the bath. And throughout this talk, I'll be assuming that these isometries can actually be unitaries, but the conclusions hold also in more general case, and just the mathematics becomes longer and requires more and more characters to introduce, which in the end don't lead to any substantially different qualitative conclusions about the scenarios. So I talked a little bit about why would we like to talk about quantum features or quantum superpositions of temperature, and so now how? I guess that the two examples that motivated the research are very much, as you would expect, one of the hints as to how. But so let me just very generally start with how, in general, we consider preparing or talking about quantum superposition. So we may have this picture where we have some initial state of the degree of freedom that we are interested in. So this is the state in, and some other degree of freedom of this system that can be put in superposition. And depending on the state, I will call it a path. It doesn't have to be a special path. The other degree of freedom is prepared in one of two states. So here it's just a cartoon where, depending on the state of the first system, the second system is prepared in state psi or phi. And you can very easily realize something like this for, say, preparation of a spin of some particle by putting this particle in some externally varying magnetic field, and you can tune the strength and the gradient of the field in such a way that during the transit time of your particle, you'll prepare some desired spin states. And then, depending on where your particle exits from the interferometer, you will conditionally have superpositions, well, the two orthogonal superpositions. And of course, I skip all the normalizations for clarity. And so we can generalize this way of thinking of how we prepare superpositions from preparing some superpositions of pure states to the case where, depending on the path, a different mixed state is prepared. So essentially, a different channel is acting on the degree of freedom of interest. So this is the cartoon here, where, depending on the state of the path, we have a different bath at some temperature, and each of these baths interacts with our probe system that will be called the thermometer or a probe, depending on how it rolls off the tongue. And then we have this superposition through the same means as pure states. So just to highlight, we talk here about two separate baths. So there are two different systems. And one thermometer that is in a usual superposition. So yeah, maybe just highlight, these are all independently prepared subsystems of some big system in encompassing the path, the probes of the system thermalizing in the baths. And this interaction that happens through the Mach-Zehnder can be thought as essentially as a controlled unitary. It's just that, depending on the control, we have the unitary, two, in principle, different unitaries, and in particular, unitaries between the system and a different bath. So that's all that we need to then answer the question, what will be an output state, let's say, in the plus port. And I'm including here some arbitrary relative phase that can also be acquired. And here you have such a general output. And it includes already the fact that the individual channels are only defined up to these isometries, the unitaries. So in general, what we get is we have terms that correspond to individual thermal states that we would get if the system only interacted with BAT1 or BAT2, the first two, and then a cross term or an interference term where both baths are relevant. And so very generally, we see from this that the final state in general is not thermal. And it depends on the temperatures of the baths, the initial state of the probe, and also on these local unitaries. This dependence on the local unitaries in other terms is known as dependence on the particular Krauss representation of the thermalization channel. And that's something that is well known in context where people look at the channel acting on a subspace rather than a subsystem, and that's what's happening here as well. Now, I would like to look at coherence here, coherence in the path degree of freedom, because this can be seen as a way to understand whether there is any coherence in this superposition of enacting the channels. And the reason one might worry that there might not be any coherence left is that we are considering here some kind of superposition where, depending on the amplitude, say, of the path, we have a different thermal state. So there is some classical parameter T that defines the state, and that in principle can be measured or known and could reveal which way information and so destroy any coherence left in the whole system. But that's not the case. But there are some interesting features to this way of looking at coherence arising from this kind of process. And so I would like to highlight that maximal coherence in this case, it's only possible if actually both baths are at zero temperature. And these local unitaries are essentially identical up to some global phase. And the system starts also in the energy eigenstate. Interestingly, also for any temperatures, we can always find some representation of the channel that will give zero visibility. And this also means that we can find such representation even if temperatures are exactly equal. And so this highlights that it's not just the temperature as a parameter, of course, that reveals the which way information, but here we have these two different systems or subsystems of some bigger bath. And of course, the which way information is predominantly encoded in with which of those two systems the thermometer is thermalizing. So let me, just checking the time. All right, let me move on to the second way of thinking in terms of how a superposition of temperatures or thermalizations might arise. And so we can, and I will explain in a moment how, we can consider the bath to be prepared in different states depending on some additional degree of freedom. And then the thermometer just interacts with such a system. And of course, we cannot meaningfully define this for some thermal states, but we can consider the following. We can consider some purification of some thermal state of a bath, and will generally have the form that you see now. Now, there are a couple of decorations that you may not have seen before when talking about purifications of thermal states. So the temperature here depends on some, it's labeled by some parameter X, but also the basis of the purification. So the basis of some ancillary degree of freedom that is used for the purification is also labeled by this additional parameter. And of course, the whole trick is then to consider that there is some quantum system where this parameter depends on the state of that system. And so again, through the usual means of an interferometer, we can prepare superpositions of such purifications. Then the interaction in this case is similar, but not identical. So depending on this path degree of freedom, we have the different purifications, but the basic interaction, there is just one bath, so there is only one bath and system interaction. But for generality, we are considering that there might be some interaction between this system and the bath ancilla subsystem, or in other ways that the bath and the ancilla can have some local evolution that might be dependent on this control degree of freedom.
Magdalena, 5 minutes.
Yeah, perfect. So the final state of the thermometer in this case, again, has two expected terms where that correspond just to your system thermalizing to the temperature of related with one or the other purification. And then there is this very lengthy cross term. Yeah, perhaps it's not too important at the moment to squint your eyes at that. So let me walk you through some general features again of this state. So first of all, if we consider the same temperatures for the purification and the same basis for the purification, then in general, the final state can be thermal. It still depends, and overall, we still have this dependence on the local unitaries, the same as for the same reasons as in the previous case. Again, coherence can be quantified by the coherence of the path degree of freedom at the end. So I just compactly package all these expression here. And just let me highlight that here the visibility could be maximal, even for non-zero temperatures, but provided they are equal, and that there is a common purification, and of course that is local unitaries that evolve the bath and the ancilla again equal up to the phase. I imagine it's quite intuitive. We have here a single system, so as long as the purifications do not provide any which way information per se, so they are common, and the temperatures are common, then essentially we have a single bath at some temperature, and so our system can both thermalize and the visibility, so the coherence of the control is not degraded. I will skip, unfortunately, for the want of time, the partial and pre-thermalization. So let me just say that all these results also hold for non-idealized cases where we consider channels that do not fully thermalize the system. And I would like to just briefly conclude that we've looked at very general features of a thermalization process for thermometers that in some sense could be in superposition of interacting or seeing different baths. We generally found that there are two different models that can describe such scenarios. And they are quite markedly different, as was highlighted through the discussion of the visibility and how the final state looks like. In both cases, the systems are sensitive to the particular dynamics of the bath, which can be interesting from some practical point of view. But the interesting next steps is essentially what the motivation was in the first place, and this is to understand what exactly a thermometer would show, for example, in the context of Tolman-Ehrenfest effect. And as you see, this will strongly depend whether one or two bath model is considered appropriate or is realized in any particular scenario. So these are some of the questions we are interested in currently. I'll finish here. Yeah, thanks for giving me this opportunity, and I look forward to any questions.
Thank you very much, Magdalena. Very nice talk. We have time for 1 or 2 questions. Please raise your hand using the raise hand feature, and I see Cisco. Please go ahead.
Hello, Magda. Nice to see you. Good talk. Thank you for sharing.
Hi. Yeah, great to see you.
I was just curious, the final states, when the beams leave, will they thermalize amongst themselves eventually? Will they come to some intermediate temperature between the 2 bath temperatures, or will they always just stay decoupled and remain in this type of superposition?
Yeah, that's an interesting question. And what we explored is essentially that the thermalization somehow happens within the interferometer, or that there is this external environment that purifies your bath, and then your system interacts with that prepared state. But of course, in some practical scenario, for example, I think that's probably close to the intuition we have, like when we have these 2 baths at different temperatures, wouldn't they start to thermalize? And we think that in practical scenarios, that's actually very likely, unless you prepare some experiment where you separately control. And otherwise, we expect, and actually there are some hints that actually, especially for something like a natural realization of the Tolman-Ehrenfest effect in some actual external environment, some genuine generalization of both models might be actually the correct one. And so somehow, starting from a concrete question, we realize that we just have to first understand how, in principle, we would talk about such scenarios. And we ended up somehow looking back to where we started, and now understanding, okay, how should we start approaching like some specific models so that we don't lose any relevant features. So I think that's one of the great questions, to which extent we could, for example, get away with considering that the baths stay at different temperature for the time that the thermometer thermalizes. Certainly there will be regimes where this could be true, and regimes where that can't possibly be the right way. And so there are some open questions there. Yeah.
Okay.
Thanks.
Thank you.
All right, then 1 more question only for now. Remember that there would be, oh, Magdalena, you may not make it to the break. I don't know, it's very late there, right? But there would be more questions if you're here at the break. And there's also, of course, Slack always.
Okay.
1 more question. Yeah. Roy, please go ahead. But that's the last question for this session.
Yes, so thank you for the interesting talk. I have basically 2 questions, but I can post them inside one. So you speak about en-route thermalization, and my question is how you superimpose due to space-time effects these thermal bases, because I think I understand if there is 1 base, if there are 2 bases considered. However, this superposition of only 1, I do not really understand. And I think the extension of these interferometers needs to be really large, right? Larger than these quantum clock considerations from Marseille interference, right?
Yeah, so maybe, yeah, because I guess I won't be able to address in all details your question, especially the first one. There are some ways one could actually talk about the Unruh-David detector in some kind of quantum space-time that would, where essentially the control degree of freedom, let's say, would decide what mass is the mass of the black hole where your detector is residing. So there are works along these lines where Josh Fu, Robman, myself, Samil show on various iterations we looked at these problems, but particularly simple realization of this could be if you simply consider superposing 2 classical trajectories, like Friedler trajectories of the detector, and you can consider some qubit that essentially decides whether your detector has this or that proper acceleration, or even has that same acceleration, but that happens at different points. And very interestingly, this actually leads to this situation where, in fact, the mathematics suggests that what happens for the Unruh-David detector in these cases is that it actually is subject to these two different purifications. And I think for people that think of in terms of Bogoliubov transformations between the modes in the space-time and how that explains the thermalization, perhaps that's the most intuitive, because then you have a different set of modes depending on where or what acceleration, and you can consider a full set of such reintegral modes, and if they would be different in the sense of like different horizons, they would have different horizons, then this would genuinely require these purifications to be different. Or if one would go through the mode expansion calculation, I think that's exactly what one would find. And that's also what we've seen kind of independent of that work through just modeling Unruh-de Witt detectors in these superpositions of trajectories. We've obtained results that suggest that this is the relevant model. What remains as a homework or a future research is to actually do the calculation with the Unruh-de Witt detector. One explicitly includes these purifications or mode descriptions so that one can put a finger on the exact elements. And that's something we haven't done yet, but from the results, I would say I can see that in that case, this purification superposition is appearing as the correct model. Okay,
Thank you very much. Yeah, I'm sorry to interrupt this, but
thank you.
Interesting. Yeah.
Yes. I know that we have further talks. Yeah, thanks a lot. And yeah,
thank you, Magdalena. Thank you. Your talk was great as usual. Please let's thank Magdalena again. Thank you very much.